In the year 2000, a team of physicists at the University of Maryland, Baltimore County, ran an experiment that should have ended a debate. Instead, it started one that nobody has been able to finish. They fired pairs of photons through a crystal and split them apart. One photon went to a detector. The other went on a longer journey through a maze of mirrors and beam splitters. The first photon arrived at its detector and was recorded. Done. Its position logged, its data frozen. 8 nanoseconds later, its twin reached the eraser apparatus. And depending on what happened to that twin, the already recorded data from the first photon changed its meaning. Not its value, the number on the printout stayed the same. But whether that number was part of an interference pattern or part of a random scatter depended entirely on a measurement that had not yet occurred when the number was written down. The experiment was published in Physical Review Letters on January 3, 2000. 5 authors: Yoon-Ho Kim, Rong Yu, Sergei Kulik, Yanhua Schiff, and Marlan Scully. It has been cited thousands of times. It has been discussed in hundreds of YouTube videos and physics blogs and Reddit threads and late-night conversations between people who have had a few drinks and are starting to wonder whether anything is real. And almost every single one of those discussions gets the central point wrong. The popular version goes like this: the future changed the past. A measurement made after the fact reached backward in time and altered what a particle did before the measurement existed. That is the version that gets clicks. That is the version that sounds like science fiction. And that version, technically, is not what the experiment showed. But here is the part that should keep you up tonight. What the experiment actually showed is worse. The standard debunking says there is no retrocausality here. Just correlations you can only see after the fact, and that is true. The no communication theorem guarantees you cannot send a message backwards through this apparatus, but the debunking quietly sidesteps a question that is far more uncomfortable than time travel. If the future did not change the past, then what did? Because something determined whether those photons behaved like waves or like particles. Something determined whether an interference pattern existed in the data or did not, and that something was not observation. It was not consciousness. It was not a physical disturbance or a measurement device or a pair of human eyes. It was information, the mere existence of information that could, in principle, reveal which path the photon took. Not information that anyone looked at, not information that anyone used. Information that existed. And when that information was destroyed, the interference pattern came back. You need to sit with that for a moment. The universe did not care whether anyone checked. It cared whether the information was available. And when availability changed, reality changed with it. After the fact. After the photon had already been detected. After the data had already been recorded. The record did not change, but what the record meant, what physical story it told, depended on something that had not happened yet. Physics has a name for the principle that wave and particle behavior cannot coexist. It is called complementarity. Niels Bohr introduced it in 1927. For almost a century, it was explained the same way in every textbook. You cannot know which slit the particle went through and see an interference pattern because the act of determining the path physically disturbs the particle. A photon bouncing off to reveal position imparts a momentum kick that scrambles the phase. Heisenberg uncertainty enforces the trade-off. It is mechanical. It is clean. And in 1982, Marlan Scully proved it was wrong. Not wrong as in the trade-off does not exist. The trade-off is real, but wrong as in the explanation for why. The mechanism everyone had agreed on for 55 years turned out to be a comforting story. The actual mechanism is something else entirely. And the actual mechanism has implications that mainstream physics has spent 40 years trying not to talk about. This is the story of that experiment, what it actually measured, what it actually proved, and what it implies about the nature of the reality you are sitting in right now. The answer involves a dead man's postcard, a crystal that splits light into twins, a choice made 8 billionths of a second too late, and a principle so strange that no interpretation of quantum mechanics can fully account for it. The principle is this: reality does not decide what happened until it has no other choice, and sometimes it waits longer than you think is possible. You already know about the double slit experiment, or you think you do. You have seen the animations. A particle approaches two slits. If you do not watch, it goes through both and creates an interference pattern on the far wall. If you watch, it picks one slit and the pattern disappears. Observation collapses the wave function. Consciousness might be involved. The universe is mysterious. You have been told this story so many times that it feels like settled knowledge. It is not settled. The word observation is doing enormous damage in that description, and it has been doing damage since 1927. When Bohr talked about complementarity, he was careful. He talked about experimental arrangements, not observers. He talked about the physical configuration of the apparatus determining which complementary aspect of reality is revealed. But over decades of popular retelling, the careful language eroded. Apparatus became observer, configuration became consciousness, and a precise physical principle became a vague, mystical gesture toward the power of looking at things. Here is what actually happens in a double-slit experiment, stripped of the mythology. You send particles toward a barrier with two openings. If nothing in the universe records which opening each particle traverses, the particles collectively build up an interference pattern, bright bands where the probability waves from the two slits reinforce each other, dark bands where they cancel. The pattern proves the particle's quantum state was a superposition, a coherent combination of going through slit A and going through slit B simultaneously. The wave function had a definite phase relationship between the two paths, and that phase relationship is what creates the fringes. Now modify the experiment. Place a detector near one of the slits, something that interacts with the particle just enough to record which slit it went through. The interference pattern vanishes. You get two overlapping blobs. Particle behavior. The standard textbook explanation is that the detector physically disturbed the particle. The interaction imparted a random momentum kick that scrambled the delicate phase relationship between the two paths. No phase relationship, no interference. Heisenberg wins. Clean and simple. But Marlan Scully asked a question in 1982 that blew the floor out of that explanation. What if you could mark which path the particle took without kicking it? Scully was not a marginal figure asking a marginal question. He was born in Casper, Wyoming in 1939. He earned his PhD at Yale under Willis Lamb, who had won the Nobel Prize for the Lamb shift, one of the most precise measurements in the history of physics. By the early 1980s, Scully was already a leading figure in quantum optics, and he would go on to accumulate virtually every major prize the field offers: the Frederick Ives Medal, the Arthur Schawlow Prize, election to the National Academy of Sciences, over 700 published papers, 2 foundational textbooks. He held positions at MIT, the University of Arizona, the Max Planck Institute for Quantum Optics, Texas A&M, and Princeton. This was not someone operating from the fringes. In 1982, Scully and his colleague Kai Druhl published a paper in Physical Review A titled Quantum Eraser, a proposed photon correlation experiment concerning observation and delayed choice in quantum mechanics. The paper proposed an experiment that would store which path information in the internal state of an atom near each slit without imparting any significant mechanical disturbance to the particle passing through. No momentum kick, no Heisenberg disruption. just a quiet recording of which path was taken, written in the quantum state of a nearby atom. The prediction was devastating. Even without a momentum kick, the interference pattern would vanish. The mere existence of which path information, recorded in a quantum system entangled with the particle, was enough to destroy the interference. The mechanism was not physical disturbance. It was entanglement. When the particle's path becomes correlated with an external quantum system, the particle is no longer in a pure superposition. It is in a mixed state. The phase relationship between the two paths, the thing that creates interference, is not scrambled by a kick. It is distributed into the correlations between the particle and the marker. The interference is not destroyed, it is hidden, spread across a larger quantum system where you cannot see it by looking at the particle alone. That was disturbing enough. But Scully and Druhl went further. They proposed that if you then erased the which path information, if you performed a measurement on the marker atom that made it impossible to determine which path the particle had taken, the interference pattern would return, not in the total data, in a subset of the data selected based on the outcome of the erasure measurement. Think about what that means. The particle has already passed through the slits. It has already hit the detector screen. Its position is recorded. And then, after all of that, a measurement on a completely different system, the marker atom, determines whether the particle's recorded position is part of an interference pattern or part of a random scatter. The information about the path is what matters, not the physical disturbance, not the observation, not the consciousness of the experimenter. The information. 9 years later, in 1991, Scully published the definitive theoretical statement with Berthold Georg Englert and Herbert Walther in Nature. The paper was titled Quantum Optical Tests of Complementarity. Its key finding, stated plainly, was that the loss of interference is due to the information contained in a functioning measuring apparatus, rather than controllable alterations of the spatial wave function. Complementarity is enforced by information, not by force, not by physics in the traditional sense of one thing pushing another thing, by the mere existence of a record. This was published, this was peer-reviewed, this was confirmed, and the implications were so uncomfortable that mainstream physics essentially absorbed the result and then stopped talking about what it actually means. Because if complementarity is enforced by information, if the universe tracks what could in principle be known and adjusts physical behavior accordingly, then the universe is doing something that has no name in physics. It is responding to epistemology, to the structure of knowledge itself. And that is not supposed to be how matter works. But before we can get to the full weight of what that implies, you need to understand the experiment that proved it. And to understand that experiment, you need to understand the man whose grief made it thinkable. John Archibald Wheeler was born on July 9, 1911, in Jacksonville, Florida. He earned his PhD from Johns Hopkins University at 21. He studied under Niels Bohr in Copenhagen from 1934 to 1935. And with Bohr, he developed the liquid drop model of nuclear fission in 1939, the paper that explained how uranium nuclei split. He was world famous before he turned 30. He mentored Richard Feynman. He mentored Hugh Everett, who proposed the many worlds interpretation. He mentored Kip Thorne, who would win the Nobel Prize for gravitational waves. He coined the term black hole. He coined the term wormhole. He coined the term quantum foam. He was, by almost any measure, one of the 5 most creative theoretical physicists of the 20th century. But the thing that drove Wheeler's deepest work was not creativity. It was grief. In the summer of 1944, Wheeler was the lead physicist at the Hanford site in Washington state, overseeing the plutonium production reactor that would supply the material for the bomb that would be dropped on Nagasaki. His younger brother Joe had a PhD in American history from Brown University. Joe had a wife and a baby daughter. Joe was fighting in Italy with the United States Army, and in late summer of 1944, a stained and battered postcard arrived at Hanford from somewhere near the front lines. 2 words: hurry up. Joe knew, in the broadest outlines, that his brother was working on something that could end the war. He did not know what. He knew it was taking too long. On October the 25th, 1944, Joe Wheeler was killed on a hillside near Florence, Italy. John Wheeler carried this for the rest of his life. In his memoir, he wrote that an atomic bomb program started a year earlier and concluded a year sooner would have spared 15 million lives. His brother Joe's among them. He could have, probably, influenced the decision-makers if he had tried. That guilt drove him into the hydrogen bomb program with Edward Teller. It drove him to direct Project Matterhorn at Princeton. But it also drove him somewhere stranger. It drove him to the question of whether the past is real. In 1978, Wheeler published a thought experiment that would become one of the most cited ideas in quantum foundations. He called it the delayed choice experiment. The setup is deceptively simple. A photon enters a beam splitter and takes 2 paths through an interferometer. At the far end, you have a choice. Insert a second beam splitter to recombine the paths, and you get interference. Wave behavior. The photon went both ways. Remove the second beam splitter, and 2 detectors tell you which path the photon took. Particle behavior. It went one way. Wheeler's twist was this: make the choice after the photon has already entered the apparatus, after it is already in flight. Quantum mechanics predicts, and experiments have confirmed with extraordinary precision, that it does not matter when you choose. The photon's behavior matches whichever configuration you ultimately select. If you insert the second beam splitter at the last possible nanosecond, the photon behaves as though it traveled both paths from the start. If you remove it at the last nanosecond, the photon behaves as though it picked one path from the start. Wheeler was explicit about the implication. We, now by moving the mirror in or out, have an unavoidable effect on what we have a right to say about the already past history of that photon. Then he pushed further. He imagined a cosmic scale version. Light from a quasar, emitted billions of years ago, bends around an intervening galaxy through gravitational lensing, 2 paths around the galaxy, arriving at Earth in the present. An astronomer today could choose to recombine the paths and observe interference, meaning the photon traveled both routes around the galaxy, or could set up 2 telescopes to determine which path it took. A choice made today in a laboratory would determine what the photon did billions of years before Earth existed. This was not speculation. In 2007, Vincent Jacques, Alain Aspect, and colleagues published the experimental realization in Science. They used single photons from a nitrogen vacancy center in diamond, an electro-optical modulator, as a switchable beam splitter, and a quantum random number generator to make the choice. The choice was space-like, separated from the photon's entry into the apparatus. The results were clean. 94% interference visibility in the closed configuration. Less than 1% error in which path determination in the open configuration. Wheeler's prediction was confirmed. But Wheeler was not just making a physics argument, he was making a philosophical one, forged in decades of private grief about time and loss, and whether the past could have been different. His journals, archived at the American Philosophical Society Library in Philadelphia, reveal a man obsessed with the relationship between observation and existence. He developed what he called the participatory universe, the idea that we are participators in bringing into being not only the near and here, but the far away and long ago. He developed the it from bit philosophy, first presented at a 1989 Santa Fe Institute conference, which held that every particle, every field of force, even space-time itself, derives its existence from information, from binary yes-no answers to observations. His famous self-excited circuit diagram depicts the universe as a giant U-shape, the Big Bang at one end, an observing eye at the other, the eye looking back at the beginning, bringing it into being through the act of observation. This was the intellectual landscape that Scully's erasure result fell into. And this was the question that the 1990 experiment at the University of Maryland, Baltimore County, was built to answer. Not whether observation affects the present, whether the future can reach back and change what the past was. The apparatus that Yoon-Ho Kim and his colleagues built is not simple, but every piece of it exists for a specific reason. And understanding the apparatus is the only way to understand what the experiment actually proved. So this is going to be precise. An argon ion laser produces ultraviolet light at 351.1 nanometers. This laser pumps a beta barium borate crystal, known as BBO, configured for type 2 spontaneous parametric down conversion. What that means in plain language is this. Occasionally, a single ultraviolet photon entering the crystal is absorbed and replaced by two lower energy photons. These two photons, called the signal and the idler, emerge at 702.2 nanometers each, exactly double the pump wavelength. They conserve the energy and momentum of the original photon, and because of the type 2 configuration, they are orthogonally polarized, one horizontal and one vertical, which allows them to be separated by a prism. Here is the critical part. The two photons are entangled. Their quantum states are correlated in a way that has no classical explanation. If you measure a property of one, you instantly know the corresponding property of the other, regardless of the distance between them. This is not because they were secretly assigned values at birth, like a pair of gloves in separate boxes. Bell's theorem, proven in 1964 and confirmed experimentally by Alain Aspect in 1982 and conclusively in loophole-free tests in 2015, rules that out. The correlations are genuinely non-local. The laser does not just illuminate the crystal uniformly. It passes through a double slit arrangement that creates two distinct emission regions on the BBO crystal, labeled A and B. Each region is approximately 0.3 millimeters wide, separated by roughly 0.7 millimeters. Each entangled pair comes from region A or region B, but the two possibilities are quantum mechanically coherent. The photon pair is in a superposition of coming from A and coming from B. Now the paths split. The signal photon travels a short path through a lens to detector D0, a scanning detector mounted on a motorized stage that moves it stepwise along the x-axis. D0 records the position where each signal photon arrives. Critically, D0 by itself cannot tell whether the photon came from region A or region B. Its data is a collection of position measurements, nothing more. The idler photon travels a much longer path. A prism deflects idler photons from regions A and B along different trajectories. Then the idler encounters a series of beam splitters, and this is where the architecture becomes precise. Beam splitter BSA sits in the A path of the idler. It is a 50-50 beam splitter, so the idler photon from region A has a 50% chance of being reflected to detector D3. If it goes to D3, the witch path information is preserved. An idler at D3 came from region A, therefore its twin signal photon came from region A. You know which slit. But the other 50% of the time, BSA transmits the photon onward to mirror MAR. Symmetrically, beam splitter BSB sits in the B path. 50% chance of reflection to detector D4, preserving witch path information. The idler came from B, so the signal came from B. The other 50% transmits to mirror MB. Mirrors MAR and MB redirect their respective photons toward a final beam splitter, BSC. This is the eraser. BSC is where the A path and B path converge and overlap. A photon arriving at BSC from mirror MA could end up at detector D1 or detector D2 50-50. A photon arriving from mirror MB could also end up at D1 or D2 50-50. And here is the key. If a photon is detected at D1, you cannot tell whether it came from MA or MB, which means you cannot tell whether it came from region A or region B. The which path information has been erased permanently, irrecoverably. The two paths are recombined and the information about which path was taken no longer exists anywhere in the universe. Detectors D3 and D4 preserve which path information. Detectors D1 and D2 erase it. And the entire idler apparatus is set up so that the idler photon's total path is approximately 2.5 meters longer than the signal photon's path. That translates to roughly 8 nanoseconds of additional travel time. The signal photon hits D0 and is recorded before its entangled twin has even reached the first beam splitter. A coincidence counter is connected to all 5 detectors. It matches each detection event at D0 with a corresponding detection at one of the 4 idler detectors using timing correlations. This sorts the D0 data into 4 subsets. R01 is the set of signal photon positions at D0 where the corresponding idler was detected at D1. R02 is where the idler went to D2. R03, the idler went to D3. R04, the idler went to D4. All 4 subsets are collected simultaneously during a single experimental run. The apparatus does not change between subsets. Every photon pair goes through the same equipment. And here are the results. Look at the total data at D0 first, without sorting. All signal photon positions lumped together. What do you see? A smooth, featureless single-slit diffraction envelope. A hump, no interference fringes, no wave behavior visible at all. If you only had D0's data, you would conclude this was a perfectly ordinary experiment, with no surprises. Now sort the data. R01, the subset where the idler went to D1 and the which path information was erased, shows a clear interference pattern. Young's double-slit fringes, bright and dark bands modulated by the single-slit envelope. The signal photons in this subset behaved like waves. They went through both slits. R02, where the idler also went to an eraser detector, also shows an interference pattern, but shifted by half a fringe spacing relative to R01. Where R01 has peaks, R02 has troughs. Where R01 has troughs, R02 has peaks. The 2 patterns are perfectly complementary. R03, where the idler went to D3 and the which path information was preserved, shows no interference. A smooth hump. Particle behavior. R04, same thing. No interference. The signal photons in these subsets behaved like particles that went through one slit or the other. The mathematics is exact. R01 follows a cosine squared distribution. R02 follows a sine squared distribution. Cosine squared plus sine squared equals 1. The 2 interference patterns cancel perfectly when combined. Add them to the 2 non-interference distributions from R03 and R04, and you recover the featureless total pattern at D0. This cancellation is not an accident. It is a mathematical necessity. And it is the reason the experiment cannot be used to send a signal backward in time. Nothing observable at D0 ever changes based on what happens to the idler photons. The total pattern is always the same hump. The interference is hidden inside the correlations, invisible until you sort the data using information about which idler detector fired. Information that can only reach you at the speed of light, or slower. But that is the debunking. That is the part physicists are comfortable saying. The future did not change the past. No retrocausality, the no communication theorem holds. Everything is fine. Everything is not fine because the debunking answers the wrong question. The question was never, can you send a message backward through this apparatus? Nobody serious ever thought you could. The question, the one that should make you deeply uncomfortable, is this. How did the signal photons know? When a signal photon arrived at D0, it was recorded. Its position was fixed. At that moment, its entangled twin was still in flight. The twin had not yet encountered any beam splitter. No determination had been made about whether its which path information would be preserved or erased. And yet, the signal photon's position was already consistent with the pattern it would later be sorted into. Signal photons whose twins would later be erased were already landing in positions consistent with an interference pattern. Signal photons whose twins would later have their which path information preserved were already landing in positions consistent with no interference. The photon did not change its position after the fact. Its position was fixed at detection, but its position was correlated from the moment of creation with a measurement that had not yet occurred. The entanglement encoded the correlation from the start. The information about which subset each photon would later belong to was woven into the quantum state from the instant the pair was born. And this is where the standard explanations start to strain, because you can say the correlations were pre-existing, and that is technically accurate within the mathematics of quantum mechanics, but pre-existing correlations with future events is not a normal thing. In classical physics, correlations come from common causes in the past. Two events are correlated because something in their shared history connects them. In this experiment, the correlation is between a detection at D0 and a detection at D1 or D3 that has not happened yet and is determined by a random process at a beam splitter the idler has not reached. You can call that pre-existing. You can say the entangled state contained these correlations all along. But what you are really saying, if you are honest about it, is that the quantum state at the moment of creation already encoded information about every possible future measurement context. The state did not specify what would happen. It specified what would happen for each possible thing that could happen later. And the universe held all of those possibilities open, simultaneously, until the measurements were complete. That is not retrocausality in the crude sense of the future sending a signal to the past. It is something more subtle and in some ways more disturbing. It is a reality that refuses to commit, a reality that maintains every option, every potential history, every possible version of what the photon did, right up until the last moment when the complete experimental context is finalized. And the thing that finalizes it is not observation, it is not a physical disturbance, it is the closure of information, the point at which path information either exists or does not exist, permanently and irrecoverably. The universe, in this experiment, does not care what you know, it cares what can be known, and it adjusts reality accordingly. And here is where it gets worse, because there is a quantitative version of this, and it has been experimentally verified, and it makes the situation far more precise and far more uncomfortable than any vague hand-waving about wave-particle duality. In 1996, Berthold Georg Englert published a paper in Physical Review Letters that formalized something physicists had been circling around for decades. He called it the duality relation. It is written as d squared plus v squared is less than or equal to 1. D is distinguishability, a number between 0 and 1 that measures how well you could, in principle, determine which path the particle took. V is visibility, a number between 0 and 1 that measures how clearly interference fringes appear. When D equals 1, you have perfect which path knowledge and V must equal 0. No interference. When V equals 1, you have perfect interference, and D must equal 0. No which path knowledge possible. But the relation also allows everything in between. You can have partial which path information and partial interference as long as the two add up correctly. This is not a philosophical statement. It is an experimentally testable equation, and it has been confirmed in multiple laboratories. And what it tells you is that complementarity is not a binary switch between wave and particle. It is a continuous trade-off governed entirely by the availability of information, not by physical disturbance, not by the uncertainty principle in its momentum kick formulation, by information. Englert gave it its sharpest form, and the delayed choice quantum eraser is essentially a demonstration of this relation in the most dramatic possible configuration, one where the information availability is determined after the particle has already been detected. Let me be precise about what information means here, because it is not what you might think. It does not mean knowledge in someone's head. It does not mean a conscious being looking at a readout. It means a physical correlation between the quantum system and some other system in the universe. When the signal photon's path is entangled with the idler photon, that entanglement is the information. It exists as a physical fact about the quantum state of the combined system. It exists whether or not any human, any computer, any detector ever accesses it. The universe does not check whether someone is paying attention. It checks whether the correlation exists. If it does, D is greater than 0, and V must decrease. If the correlation is destroyed, D drops and V can rise. This is decoherence. The word was introduced by H. Dieter Zeh in the 1970s and developed into a full theoretical framework by Wojciech Zurek in the 1980s. When a quantum system interacts with its environment, the environment becomes entangled with the system, and the system's quantum coherence, the delicate phase relationships that create interference, gets distributed into the correlations with the environmental degrees of freedom. Those correlations are effectively irreversible because the environment has an astronomical number of particles. You cannot gather all of them back together and erase the information they absorbed. The coherence is not destroyed. It is diluted into an ocean of entanglements, so vast that no practical operation could recover it. What the quantum eraser does is create a situation where decoherence has not happened yet. The which path information is stored in a single idler photon, not in an environment of billions of particles. One photon, one quantum system. And because it is one quantum system, the information can still be erased. A measurement in the right basis, a beam splitter that mixes the two possible paths of the idler, and the which path information ceases to exist. When it ceases to exist, the coherence in the signal photon subensemble is restored, not because something traveled backward in time, because the total quantum state always contained that coherence, hidden in the entanglement correlations, and the erasure measurement revealed it by selecting the right subset. That is the technically correct explanation, and if you are comfortable with it, you should not be, because there is a question buried in it that does not go away. If the total quantum state always contained the interference pattern hidden in the correlations, and the only thing the erasure measurement did was reveal it through post-selection, then what was the state of the signal photon before the idler was measured? Was it a particle? Was it a wave? Was it both? Was it neither? Quantum mechanics gives you a precise mathematical answer. The signal photon's state, considered alone by tracing over the idler subsystem, is a mixed state. It has no interference, it is not in a superposition. It is as if it went through one slit or the other, classically, with equal probability. But that mixed state is a product of ignoring the idler. If you include the idler, the total state is pure, coherent. The interference is there in the full two-photon state. It is only invisible in the reduced description of the signal photon alone. So what was real? Was the signal photon's reduced mixed state real, in which case it genuinely had no interference? And the eraser measurement later, after the fact, created the interference pattern in the subensemble? Or was the total two-photon entangled state real, in which case the interference was always there and the reduced description was just incomplete? If you choose the first option, you are saying that something that happened later created a feature that did not previously exist. That sounds a lot like retrocausality. If you choose the second option, you are saying that the reduced description of a subsystem, the local reality of the signal photon, is not real. That the only real thing is the global quantum state, which includes correlations with systems arbitrarily far away, and with measurements that have not yet occurred. That sounds like the local world you experience every day is not fundamental. That locality itself is an illusion. Neither answer is comfortable, and no interpretation of quantum mechanics fully resolves the tension. The Copenhagen interpretation says, stop asking. The wave function is a tool for prediction, not a description of reality, and questions about what the photon really did between measurements are meaningless. Many worlds says both things happened in different branches, and the correlations are just which branch you find yourself in. Relational quantum mechanics, Carlo Rovelli's framework from 1996, says there is no observer-independent state at all, that the signal photon's properties are always relative to another system, and the question of what it really was, in an absolute sense, has no answer. But these are not solutions. They are different ways of stating the problem. And the delayed choice quantum eraser is the experiment that makes the problem sharpest, because it puts a clock on the ambiguity. The signal photon is detected at time t. The idler photon reaches the eraser at time t plus 8 nanoseconds. And the physical content of the signal photon's recorded detection, whether it contributed to an interference pattern or a smooth distribution, depends on which measurement is later performed on the idler. No signal traveled backward. The no communication theorem holds. But something is going on with the relationship between time and physical reality that we do not have the language for. And the people who should have that language, the physicists and philosophers who work on quantum foundations, are the first to admit it. This is the invisible scandal. This experiment was published in the year 2000, a quarter century ago. It has been cited in thousands of papers. It is taught in graduate courses, and there is no consensus on what it means. Not because physicists are lazy, not because the data is ambiguous, because the data is so clean and so precise that it eliminates every comfortable interpretation. All that is left are the uncomfortable ones. And the fact that the physics community has no consensus would be bad enough on its own. But in 2012, a group in Vienna made it worse, significantly worse. They ran a version of the delayed choice experiment that goes beyond wave-particle duality and into the fundamental structure of entanglement itself. And the results suggest that the problem is not limited to what photons do at slits. It extends to whether quantum relationships between particles are real before they are measured. The experiment was published in Nature Physics by Xiaosong Ma and colleagues in Anton Zeilinger's group at the University of Vienna. Zeilinger shared the 2022 Nobel Prize in Physics with Aspect and Clauser for his work on entanglement. He is not a marginal figure. The paper was titled Experimental Delayed Choice Entanglement Swapping. It realized a thought experiment proposed in 2000 by Asher Pears. The setup is intricate, but the logic is clean. Two independent sources, source 1 and source 2, each produce a pair of polarization-entangled photons. Source 1 produces photons 1 and 2. Source 2 produces photons 3 and 4. Photons 1 and 4 are sent to Alice and Bob, who measure their polarizations and record the outcomes. These photons travel through short fibers, about 7 meters, and are detected approximately 35 nanoseconds after creation. At the moment Alice and Bob record their results, photons 1 and 4 are gone, absorbed by the detectors, ceased to exist. Photons 2 and 3 travel through much longer fibers, about 104 meters, to a third party, Victor. Victor's measurements occur approximately 520 nanoseconds after the photons were produced. That is, 485 nanoseconds after photons 1 and 4 were already detected and destroyed. Victor has a choice, determined by a quantum random number generator. He can perform a Bell state measurement on photons 2 and 3, which projects them onto an entangled state. Or he can perform a separable state measurement, which projects them onto a product state. When Victor performs the Bell state measurement, something extraordinary happens. The already recorded outcomes of Alice and Bob, measurements that occurred almost half a microsecond earlier on photons that no longer exist, show quantum correlations consistent with entanglement. When the experimenters go back to Alice and Bob's data and sort it based on the subset where Victor performed the Bell state measurement, photons 1 and 4 are entangled. They violate a Bell inequality with S equal to 2.37, well above the classical limit of 2. When Victor performs the separable state measurement instead, the already recorded outcomes of Alice and Bob show only classical correlations. Photons 1 and 4 were not entangled. Let that sit for a moment. Photons 1 and 4 never interacted. They came from different sources. They were measured and destroyed before Victor even made his choice. And whether they were entangled with each other, whether they shared a quantum relationship that has no classical explanation, depends on what Victor did after they were dead. The same caveats from the original quantum eraser apply here. The correlations are only visible in the subensembles conditioned on Victor's results. The total unconditioned data of Alice and Bob shows no difference between entangled and non-entangled cases. No signal is sent backward. The no communication theorem holds. But the conceptual challenge is sharper, because this is not about wave versus particle at a double slit. This is about whether the fundamental quantum relationship between two particles, entanglement itself, the thing that Bell proved cannot be explained by local hidden variables, the thing that Einstein called spooky action at a distance, can be retroactively established between particles that have already been measured and no longer exist. The MA team was explicit about the implication. They wrote that if one viewed the quantum state as a real physical object, one could get the paradoxical situation that future actions seem to have an influence on past and already irrevocably recorded events. If that is the escape hatch the mainstream uses, if you view the quantum state as real, the alternative is that you do not, that the quantum state is just a mathematical tool, not a physical thing. That entanglement is a feature of our description, not of reality. But that alternative has its own cost. If the quantum state is not real, then what is? What is the physical thing that exists between measurements? What accounts for the correlations that reliably, repeatably, experimentally violate Bell inequalities? You can say the state is not real, but then you need something else that is real, and nobody has produced a compelling candidate that avoids even worse problems. This is where the discussion typically ends in mainstream physics. With a shrug, with the phrase "it depends on your interpretation," as if the question of whether reality has a definite structure when nobody is checking is a matter of personal preference, like choosing between chocolate and vanilla. But a growing minority of physicists are not shrugging. They are taking the experiments at face value and asking what kind of theory you would need to explain them without relying on the crutch of interpretation dependence. And the answer some of them are arriving at is the one that physicists have been most reluctant to consider: retrocausality. The possibility that causal influences can travel backward in time. The earliest serious proposal came from Olivier Costa de Beauregard, a French physicist and student of Louis de Broglie. In 1947, while still a graduate student, Costa de Beauregard proposed that the correlations in EPR experiments could be explained by a zigzag causal path through spacetime. Alice's measurement sends an influence backward in time to the source. The source then sends an influence forward in time to Bob. The path is local in the sense that all influences travel along time-like trajectories at or below the speed of light. There is no faster-than-light action at a distance. But some segments of the causal path run backward in time. De Broglie initially forbade him from publishing. The idea was too radical. But after Feynman's 1948 path integral formulation, which routinely treated antiparticles as particles moving backward through time, the concept seemed less outlandish. Costa de Beauregard finally published in 1953. He was widely dismissed. He embraced the dismissal, noting that since EPR correlations are themselves a crazy phenomenon, any explanation must be equally crazy. The philosophical groundwork for modern retrocausality was laid by Hugh Price, an Australian philosopher born in 1953. Price served as the Bertrand Russell Professor of Philosophy at Cambridge from 2011 to 2200 and was the founding director of the Centre for Time at the University of Sydney. In his 1996 book, Time's Arrow and Archimedes' Point, Price argued that our instinctive rejection of retrocausality is a temporal bias, an asymmetry in our thinking that is not justified by the time-symmetric laws of fundamental physics. The laws of quantum mechanics run the same forward and backward. If we accept that a measurement at time t1 can influence the state at time t2 in the future, time symmetry demands we also accept that a measurement at time t2 can influence the state at time t1 in the past. Our refusal to accept the second while embracing the first is not physics. It is prejudice. Price exchanged letters with John Bell in 1988, sending him papers on retrocausality. Bell's response was revealing. He wrote that he lapsed quickly into fatalism when considering backward causation. Price and his collaborator Ken Wharton later argued that Bell had confused retrocausality with superdeterminism, two fundamentally different proposals. Superdeterminism says the initial conditions of the universe are fine-tuned to make it look like Bell inequalities are violated when they are not. It is conspiratorial and widely considered untestable. Retrocausality is a genuine causal structure, subject to constraints, and potentially testable. Bell, they argue, was rejecting the wrong thing. The most mathematically rigorous retrocausal framework comes from Yakir Aharonov, the Israeli-American physicist born in 1932 in Haifa. Aharonov is best known for the Aharonov-Bohm effect, demonstrated in 1959 with David Bohm, which showed that electromagnetic potentials have physical significance in quantum mechanics, even in regions where the electric and magnetic fields are zero. It was one of the first demonstrations that quantum mechanics is fundamentally non-local, even in its basic structure. In 1964, Aharonov published a paper with Peter Bergman and Joel Lebowitz in Physical Review titled Time Symmetry in the Quantum Process of Measurement. It is known as the ABL rule, and it showed something that should have gotten more attention than it did. The apparent time asymmetry of quantum measurement, the fact that we prepare states in the past and measure outcomes in the future, is not a feature of the fundamental physics. It is an artifact of how we set up our statistical ensembles. If you condition on both the preparation and the final measurement outcome, the physics is perfectly time-symmetric. Future measurements are as informative about the intermediate state as past preparations. From this, Aharonov developed the two-state vector formalism. In standard quantum mechanics, A system at any time is described by one state vector evolving forward from the initial preparation. In the two-state vector formalism, a system is described by two state vectors simultaneously, one evolving forward from the past preparation, one evolving backward from the future measurement. Together, the two vectors give a complete, time-symmetric description of the quantum system at every intermediate time. This is not a reinterpretation. It makes unique predictions. In 1988, Aharonov, David Albert, and Lev Weidman introduced weak measurements, interactions so gentle they barely disturb the quantum state, and showed that the two-state vector formalism predicts anomalous weak values, results that lie outside the normal range of eigenvalues. A spin-half particle can have a weak value of 100 for its spin. These anomalous predictions have been experimentally confirmed in multiple laboratories. Aharonov has stated his view plainly. He has said that apparently random events in quantum mechanics are caused by events in the future. This is not a metaphor for him. He means it literally. The future boundary condition, the final measurement, is as physically real as the initial preparation, and the two together determine what happens in between. John Kramer, emeritus professor of physics at the University of Washington, built a full interpretation of quantum mechanics around retrocausality. Published in 1986 in Reviews of Modern Physics, the transactional interpretation recasts quantum events as handshakes across space-time. An emitter sends an offer wave forward in time. An absorber sends a confirmation wave backward in time. The two waves combine to form a transaction that transfers energy and momentum atemporally, outside the flow of time. The collapse of the wave function is not a sudden event at a single moment. It is a process that spans the entire interval between emission and absorption, negotiated across past and future, simultaneously. Kramer's interpretation was inspired by the Wheeler-Feynman absorber theory of classical electrodynamics, which used a mixture of retarded waves traveling forward and advanced waves traveling backward to explain radiation. Wheeler himself had pioneered this idea in the 1940s with Feynman, decades before his delayed choice proposal. The connection is not accidental. Wheeler spent his career pushing at the relationship between time and physical reality, from the absorber theory to delayed choice, to the participatory universe. The thread runs straight through his work, and it begins, always, with that postcard. Ken Wharton, a professor of physics at San Jose State University, builds explicit retrocausal models using what he calls all-at-once Lagrangian formulations. In classical physics, the principle of least action says that a system's trajectory between 2 points in space-time is the one that minimizes a particular mathematical quantity called the action. The trajectory depends on both the starting point and the ending point. It is not determined by marching forward through time. It is determined by considering the entire path at once, including the boundary conditions at both ends. Wharton takes this seriously at the quantum level. His models treat quantum systems as four-dimensional boundary value problems, where both past and future conditions constrain the solution. Influences flow in both temporal directions, along time-like paths, at or below the speed of light. There is no action at a distance. There is no faster-than-light signaling. But there is retrocausality. In 2016, Wharton and his collaborators demonstrated something that addresses the most common objection to retrocausality, which is that it should allow you to send messages to the past and create paradoxes. They showed that the apparent fine-tuning required to prevent retrocausal signaling is actually a natural consequence of the underlying time symmetry. It is not an ad hoc constraint bolted onto the model. It falls out automatically from the same principle that generates the retrocausal influences in the first place. Time symmetry both enables retrocausality and prevents it from being exploitable for signaling. The defense mechanism is built into the structure. Matthew Leifer and Matthew Pusey published a key formal result in 2017 in Proceedings of the Royal Society A that crystallized the argument. They showed that if quantum theory is time-symmetric and the quantum state is real, then retrocausality may be necessary, not merely possible. Necessary. The logic is tight. If you believe the quantum state describes something real about the world, and you believe the fundamental laws do not prefer one direction of time over the other, then you are committed to the possibility that future measurements influence past states. The only way out is to deny one of those two premises. Either the quantum state is not real, or the laws are not time-symmetric. Neither exit is painless. The community working on retrocausality is small but credentialed. Besides Price, Aharonov, Kramer and Wharton, it includes Lev Weidman at Tel Aviv University, Eliyahu Cohen at Bar Ilan University, Roderick Sutherland, who developed a retrocausal version of Bohm's pilot wave theory, Peter Evans, Emily Adlam, and Ruth Kastner, who extended the transactional interpretation to the relativistic domain in a Cambridge University Press monograph in 2012. A dedicated workshop on free will and retrocausality in the quantum world was held at Trinity College, Cambridge, in July 2014, organized by Price and Matt Farr. Lee Smolin at the Perimeter Institute has explored retrocausal models within his energetic causal sets framework. The strongest argument for the retrocausal program is not that it is correct, it is that it might be necessary. Bell's theorem proved that quantum correlations cannot be explained by any theory that is both local and realistic. The standard response is to give up locality. Entanglement is non-local, action at a distance is real, even if it cannot be used for signaling. But giving up locality conflicts with the spirit of special relativity, which holds that no influence can travel faster than light. Physicists have learned to live with this tension by noting that the non-locality cannot be used to send information, so it does not violate the letter of relativity. But the tension is real. The universe is doing something non-local, and we do not fully understand how to reconcile that with a space-time structure that is supposed to be locally causal. Retrocausality offers an alternative. If influences can travel backward in time along time-like paths, then entanglement correlations can be explained without any faster-than-light influence at all. Alice's measurement sends an influence backward in time to the source. The source sends an influence forward in time to Bob. Everything travels at or below light speed. Everything respects the causal structure of space-time. The cost is accepting that the direction of time is not the direction of causation, that causes can come after their effects, that the future can shape the past. As Leifer has candidly noted, there is not yet a generally agreed upon interpretation that recovers the whole of quantum theory using retrocausality. The models are promising but incomplete. The onus, he says, is on the retrocausality community to flesh them out. But the experimental results that motivate the program, the quantum eraser chief among them, are not going away. They are getting sharper. And the question they raise, the question of what reality is doing when it tracks the availability of information across time, has not been answered by any interpretation. Here is what we know for certain from the experiments. When which path information exists, interference disappears. When which path information is erased, interference returns in the appropriate subensemble. This happens even when the erasure occurs after the particle has been detected. The correlations are real. They have been confirmed in multiple independent laboratories using different experimental configurations. And the correlations are not between the particle and the observer, they are between the particle and the information structure of the universe itself. That last phrase sounds mystical. It is not. It is a description of decoherence and entanglement in the most precise mathematical language we have. When a quantum system's path becomes correlated with another system, anywhere in the universe, In any form, the interference vanishes, not because someone looked, because the correlation exists. When the correlation is destroyed, the interference returns, not because someone stopped looking, because the correlation no longer exists. The universe is not responding to minds, it is responding to its own informational structure. And that structure extends across time in ways that our intuitions about cause and effect were never built to handle. This is what the quantum eraser actually proved, not that the future changes the past, not that consciousness creates reality, something more precise and more disturbing than either of those. It proved that reality, at the quantum level, does not have a fixed story. It does not decide what happened at a particular moment based on what existed at that moment. It decides based on the total informational context, including measurements that have not yet been performed. The story is not written until the last page has been read. And that principle, the refusal to commit, extends further than photons passing through slits. It extends to the Ma experiment in Vienna, where entanglement itself, the most fundamental quantum relationship between two particles, was retroactively established between photons that had already been measured and destroyed. It extends to every delayed choice experiment ever performed, from Jacques and Aspect's single photon test in 2007 to Manning's experiment with ultra-cold helium atoms in 2015 to Wagner's neutron experiment in 2023. In every case, the same principle holds. The physical story of what a quantum system did is not fixed at the time it happens. It remains open, editable, contingent on the full measurement context, until that context is complete. And here is the thing that the physics community does not say loudly enough. We do not understand why. We have equations that predict the results. Quantum mechanics works. It is the most precisely tested theory in the history of science, accurate to 11 decimal places in its predictions of the electron's magnetic moment. But having equations that work is not the same as understanding what they mean. Quantum mechanics tells us what will happen. It does not tell us what is happening. And the quantum eraser, more than any other experiment, exposes that gap. Think about what a working physicist does when confronted with the eraser results. They write down the quantum state, they evolve it forward with the Schrödinger equation, they compute the coincidence probabilities. The numbers match the data. They declare the experiment explained. But explained is doing heavy lifting in that sentence. The calculation assumed a quantum state that is a superposition of two photon states from regions A and B. That state contains, from the moment of creation, every correlation that will later be revealed by the coincidence counter. The interference pattern in R01, the anti-interference pattern in R02, the flat distributions in R03 and R04. All of it is in there from the start as mathematical structure in the wave function. But what does it mean for a physical system to contain, at the moment of its creation, the outcomes of measurements that will be selected 8 nanoseconds later by a random process at a beam splitter? In what sense are those outcomes contained? Are they real? Are they potential? Are they determined? Are they retroactively determined? The mathematics does not say. It gives you probabilities. It gives you correlations. It does not give you a story about what is real between the measurements. This is the measurement problem, the oldest unsolved problem in quantum mechanics, and the quantum eraser brings it into the sharpest possible focus. Because in most quantum experiments, you can wave the measurement problem away. You can say the particle was in a superposition, we measured it, and we got a result. The gap between the mathematical state and the experienced outcome is there, but it is small, it is abstract. You can go about your day without worrying about it. The quantum eraser does not let you do that. It puts a clock on the gap. It says the signal photon was detected at time t. Its position was recorded, and the physical meaning of that record, whether it is part of an interference pattern or not, was determined at time t plus 8 nanoseconds. The gap is not abstract anymore. It has a duration, 8 billionths of a second. And during those 8 billionths of a second, the reality of the signal photon's history was, in some precise and experimentally confirmed sense, not yet decided. You can hear the discomfort in the way physicists talk about this. They say the interference pattern was always there in the correlations. They say nothing changed retroactively. They say it is just post-selection. But just post-selection is doing work that it cannot support. Post-selection is a procedure you apply to data after collecting it. It is sorting. It is filing. In classical physics, post-selection never reveals patterns that were not present in the individual data points. If you flip a coin 1,000 times and record the outcomes, no amount of post-selection on a second correlated coin will turn those outcomes into a sine wave. But in quantum mechanics, post-selection on an entangled partner does exactly that. It reveals structure in the data that is invisible without the partner's information, structure that was not present in any individual signal photon's recorded position, structure that exists only in the correlations between systems. That is not just sorting, that is a fundamental statement about the nature of reality. It says that the properties of a quantum system do not belong to the system alone, they belong to the system and everything it is entangled with, including systems that have not yet been measured. The signal photon at d0 does not have a definite Witch path history. It does not have a definite wave or particle character. Those properties are distributed across the entangled state, and they crystallize only when the full measurement context is complete. The word for a reality like that, a reality that does not commit to definite properties until forced, does not exist in physics. Wheeler reached for it with phrases like the participatory universe and it from bit. Bohr reached for it with complementarity. Rovelli reaches for it with relational quantum mechanics. Aharonov reaches for it with the two-state vector formalism and its backward evolving states. None of them have found a word that captures it, because the concept is not that the universe is strange. The concept is that the universe is not the kind of thing that has a story, not in the way you think of stories as sequences of definite events happening in order. The universe is something else, something that holds all stories simultaneously and selects between them based on criteria that include the future. And the people who know this, the physicists who have worked through the mathematics and stared at the data and tried every interpretation and found all of them wanting, have mostly decided that the safest response is to keep calculating and stop asking what the calculations mean. That is not science. That is surrender. And the quantum eraser is the experiment that makes the surrender visible. But surrendering does not make the problem disappear. It makes the problem invisible. And invisible problems have a way of getting worse while nobody is looking. Consider what the quantum eraser actually demonstrated. Stripped of all interpretive hedging, a photon was detected. Its position was recorded. The recording did not change. But whether that recorded position belonged to an interference pattern or to a featureless scatter was determined by a measurement performed 8 nanoseconds later on a completely different particle. The information structure of the universe, the web of correlations and entanglements that connects quantum systems across space and time, decided the physical meaning of an already completed event. That is not retrocausality in the science fiction sense. No signal traveled backward. No message was sent to the past. The no communication theorem, proved by Philippe Eberhard in 1978, and formalized rigorously in the following decade, guarantees that local measurements on one half of an entangled pair cannot alter the measurement statistics of the other half. The math is airtight. You cannot use the quantum eraser to send stock tips to yesterday. But here is the thing that should bother you. The no communication theorem does not say that nothing happened. It says that whatever happened cannot be exploited for signaling. That is a much weaker claim than most people realize. Something determined whether the interference pattern existed in the R01 subensemble or not. Something connected the signal photon's behavior to the idler photon's fate. That something was not a signal, but it was also not nothing. It was a correlation, a structure in the entangled state that extended across time in ways that our language for cause and effect cannot capture. The standard physics response is to say the correlations were always there. They were present in the entangled state from the moment the photon pair was created in the crystal. The idler measurement did not create them retroactively. It revealed them. This is technically correct. But technically correct is not the same as explained, because what does it mean for a physical state to contain at the moment of creation patterns that will only become visible when conditioned on events that have not yet occurred? In what sense are those patterns real before the conditioning? Are they determined, potential, superposed? The mathematics gives you probabilities. It does not give you ontology. It does not tell you what is actually there. And the deeper you push on this, the stranger it gets. In 2012, a team led by Xiaosong Ma in Anton Zeilinger's laboratory at the University of Vienna published an experiment that makes the Kim experiment look almost tame by comparison. The paper appeared in Nature Physics with the title Experimental Delayed Choice Entanglement Swapping. What they demonstrated should be impossible. It is not impossible. It happened, and the implications go further than most physicists are comfortable admitting. Here is what they did. Two completely independent sources produce two pairs of entangled photons. Source 1 creates photons 1 and 2. Source 2 creates photons 3 and 4. The two sources have nothing to do with each other. No connection, no shared history. Photons 1 and 4 have never interacted with each other and were never part of the same quantum system. Alice receives photon 1, Bob receives photon 4. They measure these photons and record the results. The measurements happen first, approximately 35 nanoseconds after the photons are created. Photons 1 and 4 travel through short fiber paths, just a few meters, and hit their detectors. Done. Recorded. Frozen. At this point, photons 1 and 4 have been measured and no longer exist. They have been absorbed by the detectors and converted into electrical signals. Meanwhile, photons 2 and 3 are traveling through much longer fiber paths, about 104 meters each. They do not reach Victor, the third experimenter, until roughly 520 nanoseconds after they were created. That is almost 500 nanoseconds after photons 1 and 4 have already been measured and destroyed. Victor has a choice. He can perform a Bell state measurement on photons 2 and 3, projecting them onto an entangled Bell state. Or he can perform a separable state measurement, projecting them onto product states that are not entangled. The choice is made by a quantum random number generator. Victor does not decide. Randomness decides. And here is the result that should keep you awake. When Victor performs the Bell state measurement, the already recorded outcomes of photons 1 and 4 show quantum correlations consistent with entanglement. When Victor performs the separable state measurement, the already recorded outcomes show only classical correlations. Victor's choice, made 500 nanoseconds after photons 1 and 4 were measured and destroyed, determines whether those two photons were entangled or not. Not whether they appeared to be entangled. Whether they were entangled, entanglement is not a pattern in data. It is a physical relationship between quantum systems. It is the thing that Einstein called spooky action at a distance. It is the thing that Bell's theorem says cannot be explained by any local hidden variable theory. And in the Ma experiment, that physical relationship was established retroactively between particles that had already been measured, already been destroyed, and never shared a common past. The authors of the paper were careful in their language. They wrote that if one viewed the quantum state as a real physical object, one could get the paradoxical situation that future actions seem to have an influence on past and already irrevocably recorded events. That conditional phrasing, if one viewed the quantum state as a real physical object, is doing enormous work. It is the escape hatch. It is the place where physicists retreat when the implications get too uncomfortable. But retreating to that escape hatch has a cost. If the quantum state is not a real physical object, then what is it? A mathematical fiction? A tool for making predictions? A representation of someone's knowledge? Each of those options has consequences that are at least as disturbing as retrocausality. Let me be precise about what the Ma experiment demonstrated, because precision matters here. The experiment did not show that Victor's choice creates entanglement where none existed before. The entanglement was always latent in the 4-photon state produced by the two sources. What Victor's choice determined was which type of correlation would be revealed when the data was analyzed. Bell state measurement reveals quantum correlations consistent with entanglement. Separable state measurement reveals only classical correlations. Both possibilities were always present in the quantum state. Victor's measurement selected which one would be manifested in the analysis. But that precision does not make the result less disturbing. It makes it more disturbing, because it means the quantum state of those 4 photons from the moment they were created contained correlations that would be revealed or hidden depending on a choice made 500 nanoseconds later. The state knew, in some sense, what was coming, or rather, the state was structured in a way that accommodated all possible future choices simultaneously, with the actual manifestation waiting until the choice was made. This is the temporal entanglement that standard accounts of quantum mechanics struggle to capture. The entangled state is not just non-local in space, it is non-local in time. It contains structure that references events distributed across the temporal dimension as well as the spatial ones. And that structure is real. It produces measurable correlations. It survives the most rigorous experimental tests we can devise. The only question is what it means. Zeilinger himself has thought deeply about this. He shared the 2022 Nobel Prize in Physics with Alan Aspect and John Clauser for experiments with entangled photons. He has spent decades probing the foundations of quantum mechanics. From the first demonstration of quantum teleportation in 1997 to the satellite-based quantum key distribution experiments that have made unhackable communication a practical reality. His foundational principle, published in Foundations of Physics in 1919, states that an elementary system carries one bit of information. He has argued that the distinction between reality and our knowledge of reality, between reality and information, cannot be made. Think about what that means. If the distinction between reality and information cannot be made, then information is not just something we have about the world, it is something the world is made of. The universe is not a collection of particles moving through space according to deterministic laws that we happen to know imperfectly. The universe is, at some fundamental level, informational. And the quantum eraser, the Ma experiment, every delayed choice experiment ever performed, is a window into that informational structure, a window that shows us something we were not prepared to see. This is related to something called the holographic principle in modern physics, the idea that all the information in a region of space can be encoded on its boundary, like a 3-dimensional scene described by a 2-dimensional hologram. The principle emerged from work on black holes by Stephen Hawking, Jacob Bekenstein, and Gerard 't Hooft in the 1970s and 80s. It suggests that space-time itself may be emergent from more fundamental informational structures. If that is true, then the quantum eraser is not just showing us something strange about photons, it is showing us something about the deep architecture of reality, where information and physics are not separate categories, but aspects of a single underlying structure. The structure extends across time. It includes measurements that have not yet been performed. It determines the physical meaning of events that have already occurred. And it does all of this without violating the no-signaling constraints that special relativity demands. The universe found a way to be non-local in time without allowing time travel. It found a way to keep its options open without letting us exploit that openness. The defense mechanism is built into the structure, as Wharton and his collaborators demonstrated in 2016. Time symmetry both enables the strangeness and prevents it from being weaponized. But prevented from being weaponized is not the same as prevented from being real. Something is happening in these experiments. Something is connecting events across temporal gaps that our intuitions say should be unbridgeable. And the fact that we cannot exploit it does not mean we understand it. It means we have hit a wall. The wall is not in the experiments. The wall is in us, in our conceptual vocabulary, in the categories we inherited from a classical world that turned out to be a special case. To understand how deep this goes, you need to understand Bell's theorem, not the popular version which says quantum mechanics is spooky and Einstein was wrong. The actual theorem, which is one of the most profound results in the history of physics and which almost nobody outside of specialists understands correctly. John Stuart Bell was born in Belfast in 1928. He earned his PhD from the University of Birmingham in 1956 and spent most of his career at CERN, the European Particle Physics Laboratory in Geneva, working on accelerator physics and quantum field theory. But his foundational work on quantum mechanics was done almost in secret, during evenings and vacations, because the physics establishment of his era considered such questions unprofessional. Thinking about the meaning of quantum mechanics was for philosophers, not serious physicists. Bell thought about it anyway. In 1964, Bell published a 4-page paper in the short-lived journal Physics. The paper was titled On the Einstein-Podolsky-Rosen Paradox. It proved a theorem that Einstein, had he lived to see it, would have found devastating. The EPR paper of 1935 had argued that quantum mechanics was incomplete. Einstein, Podolsky, and Rosen constructed a thought experiment involving two particles with correlated properties. Measure one particle and you instantly know something about the distant particle without touching it. Einstein's interpretation was that the distant particle must have had that property all along. The measurement did not create it. The measurement revealed it. There must be hidden variables, properties that quantum mechanics does not describe, that determine the outcomes in advance. Quantum mechanics is just a statistical approximation to a deeper, deterministic theory. Bell asked whether such a theory could actually exist, not philosophically. Mathematically, he derived an inequality, now called Bell's inequality, that any theory based on local hidden variables must satisfy. Local means influences cannot travel faster than light. Hidden variables means the measurement outcomes are determined in advance by properties we do not see. Bell showed that any theory combining these two assumptions must produce correlations that obey a certain mathematical bound. Then he showed that quantum mechanics violates that bound. The violation is not subtle. For certain experimental configurations, quantum mechanics predicts correlations that exceed Bell's bound by over 40%. If local hidden variables are real, those correlations are impossible. If quantum mechanics is right, local hidden variables cannot exist. The experiments began in the 1970s. John Clauser, working against the advice of his mentors who told him the question was not worth investigating, built the first practical Bell test in 1972 at Berkeley with Stuart Friedman. The apparatus was crude by modern standards, assembled from surplus equipment and shoestring budgets. Clauser had to design and build much of it himself because no commercial versions existed. The results favored quantum mechanics, but there were loopholes. Maybe the detectors were not efficient enough. Maybe the measurement settings were not truly random. Maybe some hidden communication channel connected the two sides. Alain Aspect closed the most important loophole in 1982 at the Institut d'Optique in Orsay, France. Aspect was a young postdoc when he started the work, and his mentors warned him that the subject was not respectable. He went ahead anyway. The experiment took years to build. The apparatus filled a basement. The acousto-optical modulators that switched the measurement settings were cutting-edge technology, repurposed from their intended use in telecommunications. His experiment used rapidly switching acousto-optical modulators to change the measurement settings while the photons were in flight. The switches operated at 50 MHz, fast enough that no signal traveling at the speed of light could inform one detector of the other's setting. The Bell inequality was violated by 5 standard deviations. The result was definitive within the limits of the technology. Aspect later recalled that when he first saw the violation in his data, he felt a mixture of excitement and something approaching dread. The universe really was doing something that classical physics said was impossible. The definitive loophole-free tests came in 2015. 3 independent groups, in Delft, at NIST in Boulder, and in Vienna, ran Bell tests that simultaneously closed all known loopholes: the locality loophole, the detection loophole, the freedom of choice loophole. Every escape route was sealed. The Delft experiment, led by Ronald Hansen, was particularly elegant. It used entangled electron spins in nitrogen vacancy centers in diamond, separated by over a kilometer. The distance was crucial. It ensured that the measurement on one particle was completed before any signal, even at light speed, could reach the other. The detection efficiency exceeded the threshold needed to close the detection loophole, and the measurement settings were determined by quantum random number generators, ruling out any hidden coordination between the two sides. The result was unambiguous. The Bell inequality was violated by over 2 standard deviations in the Delft experiment and by larger margins in the NIST and Vienna experiments. The statistical significance was overwhelming. The violations were confirmed. The universe is not locally realistic. That phrase, not locally realistic, needs at least one of 2 things must be true. Either the universe is not local, meaning influences can connect distant events instantaneously, or the universe is not realistic, meaning particles do not have definite properties before they are measured. Most physicists accept the first option and deny the second, or accept the second and deny the first, or adopt some combination that they do not examine too closely. Bell himself said he hoped the experiments would fail. They did not. The implications of Bell's theorem have reverberated through physics for 6 decades, and they are still not fully absorbed. Most physicists accept the result and then proceed as if it did not change anything fundamental. But it changed everything fundamental. Before Bell, you could believe that quantum mechanics was a statistical approximation to a deeper deterministic reality. After Bell, that belief is no longer tenable. Whatever is underneath quantum mechanics, if there is anything underneath, it cannot be both local and realistic. Something in our intuitive picture of the world is wrong, and Bell's theorem tells us it is wrong in a way that experiments can detect. The quantum eraser sits squarely in this territory. The correlations between the signal photon at D0 and the idler photon at the erasure apparatus are Bell-type correlations. They cannot be explained by any local hidden variable theory. The signal photon does not possess a definite Witch path property that the idler measurement merely reveals. If it did, Bell's inequality would be satisfied and the correlations would be weaker than they are. The correlations are stronger. The properties are not there until the measurement context is complete. But the quantum eraser adds something that Bell's original theorem did not address: time. In a standard Bell test, the 2 measurements are space-like separated. Neither can influence the other because there is no time for a signal to travel between them. The order of the measurements depends on your reference frame. In some frames, Alice measures first. In other frames, Bob does. Relativity says there is no absolute fact about who measured first. The quantum eraser breaks that symmetry. The signal photon is measured first, definitively, in every reference frame. The idler photon is measured 8 nanoseconds later. The temporal order is not frame-dependent. It is absolute. And the correlations still exist. The patterns still appear in the subensembles. The measurement that happens second still determines the meaning of the measurement that happened first. This is why the retrocausality community exists. This is why serious physicists, people with positions at Cambridge and Tel Aviv and Princeton, are writing papers about backward causation and zigzag paths through space-time. Not because they believe in time travel, because the alternative explanations are not explanations at all. They are descriptions with the explanatory content removed. The standard response is to say that the correlations are just correlations. They do not require any causal influence in either direction. They are features of the entangled state, present from the moment of creation, revealed by the measurement choices but not created by them. This is the view you will find in most textbooks and most popular accounts. And it is true as far as it goes, but it does not go far enough. Ask what it means for a correlation to be present in a quantum state. The state is a mathematical object, a vector in a Hilbert space, an element of an abstract formalism. The correlation is a relationship between measurement outcomes that will be obtained in the future under conditions that have not yet been chosen. In what sense is that relationship present now? The mathematics tells you the probability. It does not tell you what makes the probability that value rather than some other value. It does not tell you what exists between the measurements. It gives you predictions. It does not give you reality. And predictions, no matter how accurate, are not the same as understanding. You can predict that the sun will rise tomorrow without understanding nuclear fusion. You can predict the tides without understanding gravity. You can predict quantum correlations without understanding what the quantum state describes. Physics has been doing this for a century. It works phenomenally well, 11 decimal places of accuracy in the electron's magnetic moment, the most precisely tested theory in human history. But precision is not comprehension. The quantum eraser makes that distinction impossible to ignore. There is another layer to this. The quantum eraser does not just show that complementarity is enforced by information rather than disturbance. It shows that complementarity is quantitative. Wave and particle are not binary alternatives that exclude each other absolutely. They are traded off continuously along a spectrum. The mathematics was formalized by Daniel Greenberger and Alain Yassin in 1988 and made rigorous by Berthold Georg Englert in 1996. The relationship is captured in what is called the Englert-Greenberger duality relation. d squared plus v squared is less than or equal to 1. D is distinguishability, a number between 0 and 1 that measures how well you can determine which path the particle took. V is visibility, a number between 0 and 1 that measures how clear the interference fringes are. When D is 1, full which path knowledge, V must be 0, no interference. When V is 1, perfect interference, D must be 0, no path information. But you can also have partial knowledge and partial interference. D equals 0.7 and V equals 0.7, for example, satisfies the inequality because 0.49 plus 0.98, which is less than 1. The quantum eraser moves systems along this continuum. When the idler is detected at D3 or D4, the which path information is preserved, D is close to 1, and the corresponding signal photon subensemble shows no interference, V close to 0. When the idler is detected at D1 or D2, the which path information is erased, D drops to 0, and the subensemble shows full interference, V close to 1. The trade-off is precise. It is enforced by the mathematics of entanglement, and it operates across the 8 nanosecond gap between the signal detection and the idler detection. What does this mean for the nature of reality? It means that wave and particle are not properties of the photon itself. They are properties of the photon in context. The context includes the experimental apparatus. The context includes the measurement choices. The context includes events that have not yet occurred. The photon does not have a wave nature or a particle nature sitting inside it waiting to be revealed. It has a relationship to the rest of the universe, and that relationship determines which aspect is manifested. This is what Bohr was trying to say with complementarity in 1927. But Bohr's language was often opaque, and the generations of physicists who came after him flattened his insight into something simpler and less accurate. The simple version says observation causes collapse. The accurate version says the entire experimental context, including the choice of measurement basis and the availability of which path information, determines which complementary aspect of reality is revealed. Bohr was not talking about consciousness. He was talking about experimental arrangements. The quantum eraser proved him right in a way he probably never anticipated. But proving Bohr right does not mean understanding what Bohr was right about. The experimental arrangement determines which aspect is revealed. Fine. But how? What is the mechanism? What is the physical process by which the configuration of mirrors and beam splitters and detectors reaches back through the entangled state and selects one aspect over another? This is where the theories diverge, and this is where the honest answer is that nobody knows. The many worlds interpretation, first proposed by Hugh Everett in 1957 under Wheeler's supervision, says there is no selection at all. All outcomes occur. The universe splits into branches, one for each possible result, and you end up in one branch without any way of knowing about the others. The interference pattern exists in some branches and not in others. The coincidence counting sorts the data into subensembles that correspond to different branches. Nothing is erased. Nothing is selected. Everything happens, and your experience of being in one branch rather than another is an illusion created by decoherence. Everett developed this interpretation as his PhD thesis. Wheeler supervised it. The thesis was originally titled The Theory of the Universal Wave Function and ran to 137 pages. Wheeler convinced Everett to cut it to less than 30 pages for publication, removing most of the radical philosophical content. The abbreviated version appeared in Reviews of Modern Physics in 1957. The physics community largely ignored it for decades. Everett left academia, went to work for the Pentagon, developed algorithms for nuclear targeting, and watched from the sidelines as his interpretations slowly gained traction. He died in 1982 at the age of 51, before seeing his work become one of the most discussed interpretations in quantum foundations. This interpretation has the virtue of being mathematically clean. It does not add any new physics to the Schrödinger equation. It just takes the equation seriously and accepts the consequences. But the consequences include a constantly multiplying infinity of parallel worlds, all equally real, containing copies of you who made different choices and experienced different outcomes. The interpretation trades one mystery, wave function collapse, for another, the origin of the probability rule that tells you which branch you are most likely to find yourself in. And it makes no testable predictions that differ from standard quantum mechanics. It is elegant, it is consistent, it is also unfalsifiable. The Bohmian interpretation, developed by David Bohm in 1952 as an extension of Louis de Broglie's pilot wave theory from 1927, takes a different approach. It says particles have definite positions at all times, guided by a wave function that extends through all of space. The wave function is real. The particle surfs on it like a cork on water. The reason we cannot predict which slit the particle goes through is that we do not know its initial position precisely enough. If we did, we could track it. The randomness is epistemic, a reflection of our ignorance, not ontological, a feature of reality itself. Bohm's path to this interpretation was shaped by political persecution. He had been a student of J. Robert Oppenheimer at Berkeley and had worked on the Manhattan Project. In 1949, he was called before the House Un-American Activities Committee and refused to testify against colleagues. Princeton, where he was then teaching, suspended him. He could not find another position in the United States. He left for Brazil, then Israel, then England, where he spent the rest of his career at Birkbeck College, London. His 1952 papers on hidden variables were written in Sao Paulo, in exile, cut off from the mainstream of American physics. Bohm's interpretation handles the quantum eraser without retrocausality. The photon always goes through one slit. The pilot wave goes through both and creates the interference pattern. Which path information disturbs the pilot wave in a way that destroys the interference? Erasing the information restores it. The correlations are explained by the non-local nature of the pilot wave, which connects entangled particles across space. The theory is deterministic underneath. The apparent randomness is ignorance. But Bohm paid a price for this clarity. His theory is explicitly non-local in a way that sits uncomfortably with special relativity. The pilot wave must update instantaneously across any distance when a measurement is made on one particle of an entangled pair. This does not allow faster-than-light signaling, so it does not violate relativity's letter, but it violates relativity's spirit. Einstein would not have been pleased. Carlo Rovelli's relational quantum mechanics offers yet another perspective. Rovelli argues that quantum states are not absolute properties of systems. They are relative to other systems. When Alice measures a photon, the photon has a definite state relative to Alice. But relative to Bob, who has not interacted with either Alice or the photon, the state is still indefinite. There is no God's eye view. There is no fact about the photon independent of a specification of which system you are asking about its state relative to. In relational quantum mechanics, the quantum eraser dissolves because there is no absolute fact about whether the signal photon displayed interference or not. Relative to the coincidence counter that has access to both detectors' data, there is interference in some subensembles and not in others. Relative to someone who only sees D0's data, there is just a featureless pattern. Both descriptions are correct. Neither is complete without specifying the reference system. This sounds like a cop-out, but Rovelli would argue it is the opposite. It is taking the quantum formalism seriously instead of imposing classical intuitions on it. The intuition that there must be an absolute fact about what happened is a classical intuition. Quantum mechanics does not support it. The relational view accepts this and builds a coherent ontology around it. The cost is giving up the idea that reality has a single observer-independent story. Lee Smolin at the Perimeter Institute approaches the problem from a different direction. He argues that time is more fundamental than the quantum formalism suggests. Standard quantum mechanics treats time as a parameter, not an observable. The Schrödinger equation evolves states forward in time, but time itself is not quantized, not uncertain, not subject to the same rules as position and momentum. Smolin suspects this is wrong. He has explored models where time is real and fundamental, where the future genuinely does not exist yet, and where the apparent timelessness of certain quantum correlations is an artifact of an incomplete theory. In Smolin's view, quantum mechanics may be telling us something true about the world, but it may also be hiding something. The hiddenness is in the block universe assumption, the idea that past, present, and future all exist equally, frozen in a four-dimensional space-time that we merely experience as flowing. If the block universe is wrong, If the future genuinely is open in a way that the past is not, then retrocausality is the wrong frame for understanding delayed choice experiments. The frame should be something else, something that our current physics has not yet articulated. These interpretations are all consistent with the experimental data. That is the problem. Quantum mechanics is a framework for making predictions, and it makes predictions with extraordinary accuracy. But it does not uniquely determine what exists beneath the predictions. Many worlds says everything exists and branches. Bohm says particles exist and are guided. Ravelli says only relations exist. Smolin says time exists more fundamentally than we thought. The experiments cannot distinguish between them because the experiments only produce predictions, and all the interpretations agree on the predictions. This is the measurement problem. It is the oldest unsolved problem in quantum foundations, and the quantum eraser brings it into unavoidable focus. The problem is not that we cannot predict what will happen. We can predict with 11 decimal places. The problem is that we cannot say what is happening. The formalism works. The ontology is missing, and here is where the physics community made a choice decades ago that shaped everything that followed. They chose to stop asking. The founding generation, Bohr and Heisenberg and Dirac and von Neumann, debated these questions fiercely in the 1920s and 30s. Einstein objected, Schrödinger objected, de Broglie objected. The debates at the Solvay conferences were legendary, running for days, spilling into hotel lobbies and train stations, driven by the conviction that getting this right mattered more than professional advancement. But by the 1940s, a consensus emerged. The consensus was not a resolution. It was a treaty born of exhaustion and practicality. Quantum mechanics worked. It predicted the behavior of atoms and the spectra of elements and the properties of solids. It enabled the transistor and the laser and everything that followed. And if it did not make sense, if the equations seemed to describe a world that could not possibly be real, that was a problem for philosophers. Physicists had work to do. Shut up and calculate. The phrase is often attributed to Feynman, though he probably never said it exactly that way. Some trace it to David Merman, who used it ironically. The sentiment was real regardless of the source. Asking what quantum mechanics means was discouraged. Doing quantum mechanics, applying it to atoms and nuclei and solids and fields, was rewarded. The culture pushed foundational questions to the margins. John Bell worked on them anyway, in the evenings and on vacations, and proved one of the most important theorems in physics. He continued his day job at CERN, working on particle accelerator design and quantum field theory, while spending his spare time on the questions that his colleagues considered marginal. He once said that the strangest thing about quantum mechanics was not the strangeness itself, but the fact that physicists had learned to live with it without understanding it. He wanted to understand it. But when he died in October 1990, just months before the Nobel Prize he almost certainly would have shared was awarded to others, the physics mainstream still treated his work as a curiosity. Important, yes. Foundational, yes, but not the kind of thing serious physicists should spend their careers on. That culture has begun to change. Quantum information theory, the field that gave us quantum computing, and quantum cryptography discovered that foundational questions have practical implications. Entanglement is a resource. Decoherence is an obstacle to be overcome. The measurement problem is not an abstract puzzle. It is an engineering constraint. The new generation of quantum physicists is more willing to ask what the formalism means because understanding what it means might help them build better machines. The change is visible in the literature. Papers on quantum foundations now appear in physical review letters and Nature Physics, not just in specialized philosophy journals. Conferences on the interpretation of quantum mechanics draw hundreds of attendees. Funding agencies have begun to support research that would have been dismissed as philosophy 2 decades ago. The taboo is weakening, but weakening is not the same as broken. The drivers of change include both theoretical advances and practical pressures. The theoretical advances include new interpretations, new no-go theorems, new ways of thinking about the relationship between quantum mechanics and space-time. The practical pressures come from quantum technology. When you are trying to build a machine that exploits superposition and entanglement to solve problems that classical computers cannot, you start to care about what superposition and entanglement actually are. The questions that seemed idle turn out to have engineering consequences. The old guard still controls hiring committees and grant panels. The incentive structure still rewards applications over foundations. A young physicist who publishes on quantum computing has a career. A young physicist who publishes on what the wave function really means has a hobby. The culture is changing slowly, and the change is not complete. But the willingness to ask does not mean the answers have arrived. The quantum eraser sits there, a clean and definitive experiment, replicated in multiple laboratories, confirming results that nobody fully understands. The correlations are real. The information tracking is real. The temporal structure is real. Something connects the signal photon's behavior to the idler photon's fate across an 8-nosecond gap. That something has been given many names: entanglement, non-locality, complementarity. Information, none of the names are explanations, they are labels for a phenomenon that refuses to fit into the categories we have. And here is the part that brings us back to where we started. To Wheeler and his postcard. To the question of whether the past is fixed, Wheeler spent the last decades of his life pushing on the relationship between observation and existence. After retiring from Princeton in 1976, he moved to the University of Texas at Austin, where he continued to work on quantum foundations until shortly before his death. He was known for asking questions that other physicists found embarrassing. How does the quantum get into the classical? Why the quantum? Is existence a participatory act? He wrote on whiteboards and filled notebooks and organized workshops where the questions were not allowed to be tabled. His delayed choice thought experiment was designed to show that the past is not settled until the present makes it so. The cosmic version, where light from a quasar travels billions of years and the choice to observe it as wave or particle is made now by us, implies that our observations today are participators in bringing into being the ancient past. Wheeler called it the participatory universe. He drew a diagram of a U, the universe, with an eye at one end looking back at the Big Bang at the other end, and the acts of observation connecting them across all of time. The quantum eraser seems to support Wheeler's vision. The signal photon's behavior is not fixed at the moment of detection. It is contingent on the full measurement context, including the idler measurement that happens later. The past, at the quantum level, is not a fixed sequence of events that determined what followed. It is a network of possibilities that crystallize into definite outcomes only when the informational structure is complete. But Wheeler's vision was always controversial, and the controversy runs deeper than most popular accounts admit. The delayed choice experiments show that certain quantum properties remain indefinite. Until measurement, they do not show that macroscopic history is retroactively malleable. The transition from the quantum to the classical, from indefinite supposition to definite outcome, is governed by decoherence, the process by which quantum systems become entangled with their environments and lose their coherence. Decoherence is fast. It is effectively irreversible. It is why you do not see cats that are both alive and dead, even though the equations of quantum mechanics permit such states. The quantum eraser works because the which path information is stored in a single quantum particle, the idler photon, which is carefully isolated from the environment. As long as that photon has not become entangled with anything else, its quantum state can be manipulated, and the correlations can be revealed through coincidence counting. But if the idler photon had interacted with even a few air molecules, if its witch path information had leaked into the environment, the erasure would fail. The coherence would be gone. The interference patterns would never reappear. This is what Wojciech Zurek and H.D. Zeh formalized in their work on decoherence. When a quantum system interacts with its environment, the environment acts as a continuous measurement device, recording witch path information in an uncontrollable and practically irreversible way. The information spreads into trillions of environmental degrees of freedom. It cannot be erased. The off-diagonal elements of the density matrix, the mathematical terms that encode quantum coherence, are suppressed to negligible values within femtoseconds. What remains is a diagonal density matrix, indistinguishable from classical probabilities, describing a system that has one definite property or another, never both. The speed of decoherence is staggering. For a macroscopic object at room temperature, a grain of dust, say, the decoherence time is about 10 to the minus 30 W1 seconds. That is a trillionth of a trillionth of a trillionth of a second. The environment records the dust particle's position so fast that no experiment could ever catch the superposition. For larger objects, it is even faster. For a human being, the superposition of being in two places at once would decohere in less than 10 to the minus 40 seconds. The universe measures you, constantly, with everything around you, the air molecules, the photons, the gravitational field. Every interaction is a recording, and every recording destroys the coherence. This is why Schrödinger's cat was never both alive and dead, not for any appreciable time. The cat is made of trillions of atoms, each interacting with the air in the box, with the walls, with the radioactive source, with everything. Decoherence happens faster than any process could keep up with. The superposition exists, in the mathematical sense, for a duration too short to measure. Then the cat is one thing or the other, determined by which path information that has already spread irreversibly into the environment. Decoherence is why the quantum world seems to give way to the classical world at macroscopic scales. And decoherence is why Wheeler's participatory universe, taken literally, probably does not describe the macroscopic past. The history of galaxies and stars and planets and people is not indefinite, waiting for future observers to bring it into being. It was decohered billions of years ago. Its quantum possibilities collapsed into definite classical facts by the relentless interaction with environmental degrees of freedom. But the quantum eraser shows that decoherence is not absolute. It is contingent on the structure of the entanglement. When the witch path information is stored in an isolated quantum system, and when that system is measured in a basis that erases the information, coherence is restored, not globally, in the appropriate subensemble, but restored nonetheless. This is the principle that underlies quantum error correction, the technique that makes quantum computing possible. Quantum computers are incredibly sensitive to decoherence. Any interaction with the environment scrambles the delicate superpositions that make quantum computation powerful. A single stray photon can destroy a calculation. A single air molecule can collapse a qubit. The challenge of building a quantum computer is fundamentally a challenge of keeping quantum information isolated from the environment long enough to do useful work. But if you can encode the information redundantly, spread it across multiple qubits in a clever way, you can detect when errors occur and correct them before the computation fails. The witch path information that would destroy the quantum state is detected and erased before it can do damage. The coherence is preserved. This is not a hypothetical. Working quantum error correction codes have been demonstrated in laboratories around the world. Google, IBM, and others are racing to build machines that use these codes to perform computations that classical computers cannot match. The quantum eraser is, in a sense, the simplest possible example of this principle. It shows that the universe's commitment to definite outcomes is conditional. It depends on the structure of the information, it depends on what is recorded and what is erased, and it depends, sometimes, on measurements that have not yet been performed. What are the implications for reality? They are not comfortable. If the universe does not commit to definite outcomes until forced, then the past is not what we think it is. It is not a sequence of events that happened and are now over. It is a network of correlations that remain open to reinterpretation until the full context is complete. The events that feel finished to us, the choices that feel made, the history that feels settled, are settled only to the extent that decoherence has closed off the alternatives. And decoherence is a matter of degree. It is fast and nearly complete at macroscopic scales. But at the quantum level, in the 8 nanosecond interval between a signal photon hitting its detector and an idler photon reaching the eraser apparatus, the alternatives remain open. The past is still in play. Does this mean you could change your own past? No. The no communication theorem forecloses that. The correlations cannot be exploited for signaling. Whatever is happening across the temporal gap, it is not under your control. It is not accessible to your choices. It is a feature of the structure of quantum mechanics, not a tool for rewriting history. But the question of what you could do is not the same as the question of what is real. The correlations are real. The temporal structure is real. The fact that the physical meaning of an already recorded detection event is contingent on a future measurement is real. These are not features of our ignorance. They are features of the world, and they are features that our conceptual vocabulary, built for a classical world of billiard balls and deterministic trajectories, cannot accommodate. The quantum eraser does not prove retrocausality. It does not prove that consciousness creates reality. It does not prove that the future changes the past in any usable sense. But it does prove something. It proves that the relationship between events, between measurements, between the data points that we collect and the stories we tell about them, is not what we thought. The universe is not telling a story in the way we expected. It is doing something else, something that involves information and entanglement and temporal structures that we do not yet have the words for. And the people who should be explaining this, the physicists who understand the mathematics and have seen the data, have largely chosen to keep quiet. Not out of conspiracy, not out of professionalism, out of the culture that rewards calculations over interpretations and predictions over understanding, out of the sense that admitting we do not know what quantum mechanics means would undermine the authority that lets physics departments ask for funding. But authority purchased with silence is not authority. It is stagecraft. And the quantum eraser, a clean experiment you can build with commercial equipment, replicated across the world, consistent with everything we know about physics, is the experiment that pulls back the curtain. Behind the equations, behind the 11 decimal places of accuracy, there is a question that nobody has answered. What is the universe doing when it keeps its options open across time? What is it doing when it tracks information structure and adjusts physical behavior accordingly? What is it doing in those 8 nanoseconds when the past is not yet the past? We do not know, and the disturbing part is not that we do not know. Ignorance is forgivable. The disturbing part is that we stopped asking. We declared the question unanswerable, or unprofessional, or metaphysical, and we went back to calculating. The quantum eraser sat there demonstrating something profound about the nature of reality, and the mainstream response was to file it under curiosities and move on. He spent the final decades of his life pushing at the edges, drawing diagrams of eyes and universes and participation, trying to articulate what the experiments implied about time and existence, and the role of the observer. He never found a complete answer. He knew he would not, but he kept asking because the question was too important to let professionalism silence. In the summer of 1944, a postcard arrived from Italy. 2 words: hurry up. Wheeler spent the rest of his life trying to understand time, not just the physics of it, the meaning of it, whether it flows, whether it can be changed, whether the choices we make now reach backward as well as forward. The quantum eraser says the answer is more complicated than yes or no. It says the relationship between now and then, between cause and effect, between what happened and what it means, is not the relationship we thought. It says the universe tracks information across temporal boundaries in ways that our categories cannot capture. It says the past is not a fixed stage on which the present performs. It is something stranger, something that remains entangled with the future in ways we are only beginning to measure. Wheeler died in April 2008 at the age of 96. He had spent 60 years pushing at the boundaries of physics, from nuclear fission to black holes to the foundations of quantum mechanics. The postcard from his brother is still in the archives at the American Philosophical Society Library in Philadelphia. The question it raised, whether time could be different than we thought, whether hurrying up could change what already happened, is still open. And the quantum eraser, a machine that seems to erase the past by changing the future, keeps running in laboratories around the world, producing data that confirms everything we predicted and explains nothing at all. The universe does not decide what happened until it has no other choice. Sometimes it waits until after you think the decision was made. And when you finally look back at what happened, you will find that it was never quite what you thought. Not because the data changed. The data never changes, but because what the data means, what physical story it tells, what reality it describes, depends on things you have not done yet. That is what the quantum eraser proved. That is what the physics community has tried to absorb and failed. That is what you now know, sitting there, reading this, thinking about the choices you made today, and wondering in some new and uncomfortable way whether they are finished yet. They might not be. The universe has not decided. And neither, it seems, have you. Consider what that means for everything you think you know about causation. You learnt in school that causes precede effects. You learnt that the past determines the future. You learnt that events, once they happen, are over. The quantum eraser does not falsify these principles at macroscopic scales. Your decisions yesterday really did shape your situation today. The coffee you drank this morning really did enter your bloodstream before you felt its effects. At the level of your daily experience, causation flows forward and the past is fixed. But underneath that experience, at the level where the machinery of reality operates, things are different. The past is not a sequence of completed transactions. It is a web of correlations that remain interpretable in multiple ways until the full measurement context is complete. And the full measurement context can extend into what you would call the future. 8 nanoseconds in the Kim experiment, 500 nanoseconds in the Ma experiment. In principle, there is no limit. The only constraint is decoherence, the leakage of quantum information into the environment that makes the alternatives irretrievable. Physics does not tell you that you can change the past. It tells you that the past, at the quantum level, is not the kind of thing that comes in versions that could be changed. It is not a fixed movie that plays forward from the Big Bang. It is something else, something that does not fit into the temporal categories that evolution gave you for survival on the African savanna. Your ancestors did not need to understand quantum mechanics to avoid predators and find food. They needed to understand that the lion was there or it was not, that the fruit was ripe or it was not, that the past was fixed and the future was uncertain. Natural selection optimized your brain for that world. And then physics discovered that the world your brain was optimized for is a limiting case of something stranger. The quantum eraser is a window into that strangeness, not a window into time travel, not a window into consciousness creating reality, a window into the actual structure of physical existence, which turns out to involve information in ways that the 19th century physics of particles bouncing off each other did not anticipate, and the 20th century physics of wave functions only partially captured. Information is not a side effect of physical processes. It is woven into the fabric of those processes in ways that determine outcomes. The Landauer principle, established by Rolf Landauer at IBM in 1961, proved that erasing information has a minimum thermodynamic cost. Information is physical. The quantum eraser proved that the existence of information, not its observation, not its processing, just its existence, changes physical behavior. The two results converge on something that physics has not yet named, a principle about the relationship between reality and information that goes deeper than either classical physics or standard quantum mechanics. Wheeler called it from bit. Every particle, every field of force, even space-time itself, he said, derives its meaning from binary answers to yes or no questions posed by observations. The universe is not a collection of things. It is a network of answers to questions. And the questions, in a delayed choice experiment, can be asked after the thing has happened and still determine what the thing was. That is not mysticism. That is the content of a peer-reviewed paper in Physical Review Letters, confirmed in laboratories on 4 continents, consistent with every prediction of quantum mechanics, and still not explained by any interpretation. Wheeler was reaching for something real. The fact that he reached for it with language that sounded poetic does not mean the target was imaginary. It means the technical vocabulary did not exist. It still does not exist. That is the honest state of physics in the 21st century. The equations work, the predictions are confirmed, the underlying reality is unknown. Not unknown in the sense that we need more data, we have plenty of data. Unknown in the sense that we do not have the concepts. The categories we inherited from classical physics, categories like object, property, cause, effect, before, after, these are approximations. They work at certain scales and fail at others. Quantum mechanics is where they fail. The quantum eraser is where the failure becomes visible. And the question that remains, the question that Wheeler kept asking, and that the physics community keeps avoiding, is what replaces them? What concepts do we need to describe a reality where information determines physical behavior, where correlations span temporal gaps, where the past is contingent on the full context of measurement, where the story is not written until all the chapters are complete? What language do we need for a universe that does not work the way we thought? Nobody knows. The people who should know have decided that the question is not their department. They are working on useful things. Quantum computers, quantum cryptography, applications of entanglement that might change technology without requiring us to understand what entanglement is. That work is legitimate, it is funded, it produces results you can count. But it is not the whole story. The whole story would include what the mathematics means. It would include an account of reality that does not treat the quantum formalism as a black box that turns inputs into predictions. It would include an answer to the measurement problem that does not hand-wave about decoherence or retreat into many worlds, or appeal to consciousness. It would include an explanation of why the universe cares about information. It would include an ontology, a theory of what exists that makes sense of the quantum eraser. We do not have that story. We have fragments. We have interpretations that are consistent with the data, but wildly inconsistent with each other. We have a culture that discourages asking the foundational questions because the questions are too hard and the answers might not be tenure-worthy. We have the greatest predictive machinery in the history of science, connected to no picture of the world that a human being could live in. The quantum eraser sits at the center of this mess, clean and precise and utterly undismissed. It works. It has been replicated. It produces exactly the correlations the equations predict. And it demonstrates beyond any reasonable doubt that the nature of physical reality is not what you thought. The photon was detected. The record was made. And then, 8 nanoseconds later, in a different part of the laboratory, a measurement on a different particle determined whether that record was part of an interference pattern or not. The measurement did not change the record. It changed what the record meant. And what a record means is not a minor philosophical nicety. It is the question of what happened. It is the question of whether interference occurred. It is the question of whether the photon went through both slits or just one. These are physical questions. They have physical answers. And those answers were not determined at the moment of detection. They were determined 8 nanoseconds later. The universe waited. It held its options open. It tracked the information structure across the temporal gap, and then, when the context was complete, it committed. You can call that a correlation. You can call that standard quantum mechanics. You can call that nothing special if you run your equations and get the right numbers and do not ask what the numbers describe. But if you ask, if you push, if you demand to know what is happening underneath the predictions, you will find a void where the explanation should be. The void has been there for a century. The quantum eraser makes it impossible to ignore. And that is what you are left with. Not a mystery in the soft sense, where we just do not know yet, and more research will help. A mystery in the hard sense, where the thing we do not know is the kind of thing that our conceptual vocabulary may not be able to express. The relationship between present and past, the role of information in physical processes, the meaning of a measurement. These are not gaps in our knowledge, they are gaps in our language. And the quantum eraser, a tabletop experiment with a laser and some crystals, is the instrument that reveals them. Wheeler spent his life chasing this. He never caught it. Bell spent his evenings on it and died without recognition. Scully designed an experiment that proved complementarity is about information, and the physics community absorbed the result and declined to discuss the implications. Zeilinger won a Nobel Prize for experiments that confirm everything we know and explain nothing we need to understand. The data accumulates. The questions persist. The answers do not arrive. But the photons keep traveling through the apparatus. The coincidence counters keep sorting the data. The interference patterns keep appearing in the sub-ensembles where the witch path information was erased. And somewhere in those patterns, in the structure of the correlations, in the 8 nanosecond gap between detection and determination, there is something about the nature of reality that no one has found the words for yet. Maybe you will be the one who finds them. Maybe the concepts we need are simpler than we think, hiding in plain sight, waiting for someone to notice. Or maybe the truth is harder than that. Maybe the universe really is stranger than we can imagine, built on principles that human brains were never designed to grasp. Either way, the quantum eraser will still be there, the experiment that seems to erase the past by changing the future, the demonstration that information matters in ways we do not understand, the proof that reality, at its foundations, is not the story we tell ourselves. That story is comforting. It has a beginning, a middle, and an end. It flows from past to future. It locates you in time and gives your choices meaning. The quantum eraser does not take that story away. At the scale where you live, the story still holds. Your yesterday is over. Your tomorrow has not happened. Cause still precedes effect, and the coffee still warms your hands. But underneath the story, at the level where the machinery runs, there is something else. Something that involves correlations across time. Something that tracks information and adjusts physical outcomes accordingly. Something that does not decide what happened until it has no other choice. And sometimes its choice comes after yours. You might want to remember that, the next time you think the past is settled. The data does not change, but the data is not the whole story. The story includes patterns that only appear when you know how to look, and how to look depends on measurements that might not have happened yet. The universe is patient. It keeps its options open, and in the laboratories where the photons fly and the coincidence counters click, it reveals just enough of its structure to prove that we have not understood it yet. The rest, it seems, is still up for grabs.